Good evening, everybody. Let's get started. So for assignments coming up this week, you have no pre-lab 10. So there's no pre-lab 10 due this week, but lab 10 will start this week. And I'll explain more about lab 10 at the beginning of this lecture. There's also a quiz posted, and that is due on November 20th. So take a look at that. That is on Canvas. And go ahead and jump on Slack if you have any questions. Remember, you have to search for channels on Slack. I can't add you automatically, so you have to add yourself to the different channels on Slack now. My office hours will be right after class if you want to join to ask questions or just listen to conversation. And the TA's office hours are posted on Canvas. And as always, if you have a question during lecture, I'm happy to answer. Just go ahead and unmute or shoot a chat. And otherwise, please stay muted so we can keep the background noise low. So what I want to start with today is a lab preview. So this is your last lab, and this will be a lab that actually lasts a couple weeks. So you'll have 2 weeks to do this lab, and I'll post the details on the due date and the assignment. It's not up there yet, but I wanted to show you what you're going to be doing with this lab. It's a little more of your design than just walking through kind of a rote lab. This is an opportunity to do some electronics design with what you know now. So what you're going to be doing during lab 10 is designing and building an infrared remote control tester, okay? And well, also this could be considered an infrared sensor for a security system. There's actually many applications for infrared emitters and detectors. And so I'll show you what I mean by this, but this will be the topic of your design, your lab. So you're going to build an infrared emitter circuit. You're going to build an infrared detector circuit, and you're also going to be designing and using comparator circuits. So this is going to, I'll show you how this relates to what you've done already, but you've actually done a lot of this so far in this class. And so this is going to be primarily your design with some guidance. I'm going to provide you with a block diagram, give you some hints and tips, but everybody's answers, values for resistors, for example, and maybe some design choices are going to be different across the whole class. So you actually now have all the circuits knowledge and electronics knowledge that you need to create your own design of this infrared remote control tester, and I'll show you what I mean. So let's take a look at some of the components you'll be using. You're going to be using an infrared emitter LED. So this is essentially a diode. It's like the light emitting diode you've used in another lab, except you can't see the light coming from it. It's infrared. So you have to check it with other means. You have to check if current's flowing through this diode by measuring voltages, etc. And I'll show you, you can actually see if you have a certain kind of camera without an infrared filter on it. You can see this infrared light with a camera. You'll also be using an infrared phototransistor. And so a phototransistor is really just like a transistor, except there's no base. The base current is controlled by the light impinging on a window there. So the light intensity actually controls the collector current, but otherwise it works a lot like a transistor. And then you'll be using, instead of a specific op-amp IC to create a comparator, you're going to use a specific a comparator IC, this LM339. So you have one of those in your kit. So let's take a look at what this is going to be in terms of a block diagram. So let's start with the infrared detector. The infrared detector is going to, well, detect infrared light with that phototransistor. It's going to output an analog signal that is proportional in some way, actually just a function of light intensity. And then you're going to have two comparators, and their job is to do this. It's to indicate, using an LED, the presence of infrared light with a red LED, and I'll say the absence of infrared light with a yellow LED. So when there's infrared light present at the detector, the red light will light up. When there's no infrared light present, the yellow LED will light up, just to show you that the circuit is active and it's doing what it's supposed to be doing. There will be a green LED that's going to show you that the power is on. The LED tester, the infrared detector tester is on. And you're going to, for testing purposes, and well, maybe for the security sensor application, you're also going to build this infrared emitter. So the infrared emitter, you're going to light that up in order to test the detector, and the red light over here should turn on. When you turn off the infrared emitter or point it away, then the yellow light should be on. I'll show you an example today. If you take just a remote control from your television, most remote controls use infrared light out of the front. You'll see an LED usually sticking out of the front. And you're going to use this circuit to observe the pulses coming out of your TV or other devices remote control. So if you have a remote control, I'm sure you have many things with a remote control. Great. If not, come talk to me. We'll figure something out. But you know, grab a remote control from one of your devices or your neighbor or something like that, and we'll use that as a test device.
Professor?
Yes.
I know we're going to get more into the specifics in the actual lab, but when would the case be that the infrared emitter would be off while the sensor and circuits are still on?
Well, oh, you mean like when would the yellow LED be on? That kind of the question, or?
Yes.
Yeah. So it's like you turn on the infrared detector, and you know, your power light's going to light up, but these red and yellow LEDs, I'll say, will be complementary. In other words, if you shine the infrared sensor at the detector and turn it on, the red LED should light up. If you don't see it light up, right, a couple things could be wrong. Well, you might not be above the detection threshold set by the comparator, or the circuit might be disconnected, broken, something like that. So in which case, you'd want to see the LED light up. The yellow LED should be lit up when there's no infrared, just as sort of a sanity check, and then the red LED will light up when infrared light is present.
Okay. All right. Thank you.
So, whoop, I have the wrong camera on here. Let's go to the other camera. Okay, here we go. So what I'm going to do is I'm going to bring up some, I'm going to bring up that block diagram at the same time that I have the circuit shown and some of the AD2 software windows shown. So you saw the block diagram. If you look to the right, you see the actual circuit with conveniently paper strips put over the component values, because you get to design it on your own and it's going to be your unique design. So let me walk you through what these parts look like. You have these in your kit. Where the mouse is right now, that clear LED looking device is the infrared emitter. It's just a diode. It looks a lot like an LED. So I'm gonna kind of show this to you here, if I can get it into view. So this is just, right, it looks like an LED. It looks like a clear LED, but when you pass current through this LED, you don't see anything light up. You don't actually see any light, except there is light. You just can't see it with your eyes. So that's a diode. You know how to control current through a diode, right, with a resistor in series. So you've done that. You come over here on the right, this is the infrared photo transistor. So this is the detector right here. And again, I will give you some guidance on how to use this. And I don't know, there's what, maybe 3-4 inches separating these two. So light's being emitted on this side, it's being detected over on this side, and it's producing an analog signal, and I'll show you that on the scope down here. So that device, if I can bring it a little closer, it looks like this. It looks like another LED, but actually it's just a package that looks black, and it has a collector and an emitter terminal on it. There's no base. The base is actually controlled by the current coming from the let's see, that work? Yeah, coming from the light impinging on the device. This device, it looks black, but it's actually not black. That's transparent mostly to infrared light, and it looks black because it's blocking visible light. So that's meant to keep the interference down from visible light. Okay, and as you, let's see, come up here, this chip is the comparator chip. So this is the LM339. So when you grab a comparator chip out of your kit, make sure it's the LM339 and not the op-amp chip. And again, that will be in the guidance here. So that's the circuit. There's some power applied, so 5 volts and ground, and distributed to these components. And again, I'll give you some guidance on that. 2 of the comparators of the 4 in this chip are used for the circuit, right? For comparator 1 and comparator 2. And so what you're going to do is, well, what I did here, you have your choice. You could use your equipment however you want, but right now I have this emitter off, and so the detector is not detecting any light. So this yellow LED right here is lit up. That means the circuit's working, the detector's there, the detector's outputting a valid low signal, right? It's not falsely detecting anything. And the red light is off, and the green light indicates there's power. So this is a good condition to be in. I'm actually powering this LED, this infrared LED, the emitter, with this waveform generator that we have in the AD2. So what I'm going to do, I've got it connected, and I've got a 0% duty cycle, or 0% symmetry, as they call it. And you can power a few milliamps. I think I'm powering about 10 milliamps to this LED when I energize that circuit. If I go to 100% duty cycle, like watch the yellow line and watch what happens. Right? So the red LED turns on because there's infrared light. Again, you can't see it, but it's there. This detector is detecting it, and the red LED is on. And so what do I mean by a security sensor? So you could imagine if you wanted to detect people crossing a path, you could separate these by a couple feet. It'll work fine, a couple feet, 3 feet, 4 feet apart. And then if I take my hand and I break the beam, right, the yellow light comes on, the red light comes on. So now I'm blocking IR light. I'm not blocking IR light, right? So incidentally, you can also measure the speed of a motor like this too by measuring maybe a slot in a disc attached to a motor shaft, but lots of applications for this. So you can see that's kind of the first step. Get this part to work. Then what I want to show you is, okay, so if I change this duty cycle to, I don't know, 50%, let's just type in 50% here. You'll see on the scope, I have 2 traces. The yellow is actually the output of the photo detector, the photo transistor, and the blue is the output of the comparator. You can see it's nice and squared off. So what the comparator is doing, it's comparing the yellow trace, right, the voltage out of the detector, to a really low threshold, like a 1/4 volt. That's what this trigger is set on down here. And so, so you see you can see both lights look like they're on. Well, that's because this the infrared light is turning on and off at a kilohertz, so it just looks like they're both constantly on. If I go down to, let's say, I don't know, 1 hertz here. Let's go down to 1 hertz. You should be able to see on your screen in a minute the light flashing. So I'm looking at the light flashing. Unfortunately, my other Zoom computer is not showing the light flashing. Are you guys seeing the light flashing?
Yeah, we see it.
Okay, good.
Yeah, we.
Okay. Okay, good. So So they're alternating at a 1 hertz rate. So if I, so that's just showing that it's detecting light again, infrared light. If I go back, let's go do this. Let's turn that infrared emitter off. So I'm going to go to 0% duty cycle. So now I have the solid yellow light. And again, let me know if your video stops, if what I'm describing isn't what you're seeing. So here we have the yellow light on, there's no infrared light. Well, if I take let me get rid of one of the screens here. If I take a remote control, right? So this is a remote control, just I have a bunch of them here. And you can see, if you can see that, look in the end, that's an infrared emitter. That's an LED right there, right, coming out of the end. So if I point at the device, right, you'll see the red lights up. The red's, well, yeah, the red's blinking. You might be able to see it. You can definitely see that on the scope. What these remote controls do is they pulse light, and there's a microprocessor, microcontroller on the other end at the television or at whatever's receiving the IR to decode those pulses, to look at the timing of those pulses and decide, is it volume up, is it volume down, is it channel up, is it channel down? And so you can see that in the scope. Okay, so that would be testing the remote control. I've tested this with numerous remote controls, a Samsung, an LG, kind of a Roku remote control, and so they all work, right? So you'll see different pulses, but they all cause pulses to happen. If you have something like an Amazon, this was the Fire Cube or something like that. Some of these buttons actually control an infrared remote control, and some of these buttons don't. And I think it's either RF or ultrasonic. So you might try, if you have one of these, a few of the buttons to see, again, this plus button does something, and kind of this disc doesn't do anything. So you got to find out which buttons on your remote control, if you have an Amazon remote control, actually emit infrared light.
Professor?
Yes.
Why is it that with the remotes, when the red LED turned on, the yellow one didn't turn off?
Well, on my end, it looks like it. So you've got kind of the stroboscopic effect and low sampling going on with what you're seeing. What I see now is I see that when the red light goes on, when it blinks on, the yellow light goes off for that duration. In the video, it doesn't look like that because these pulses are so short. But when you get to it on your board, I think you'll notice it. I think you'll notice both are flashing.
Okay, all right, thank you.
Yeah. Mm-hmm. Okay, so that's what you're going to be building. You can imagine this is also good for infrared data communications. You could connect a serial port or serial data from a PC or other device up to an infrared emitter and transmit data over the air to an infrared detector, and lots of neat things you can do with this. Okay, so you'll see that coming up in lab this week. So look for that on Friday. All right, any other questions on that?
Just to confirm, even though the lab starts this week, there's no pre-lab for it?
That's right, no pre-lab due this week.
Okay, so just kind of begin the lab and then the report will be due 2 weeks from Friday?
Yeah, it's going to be due. I'll pick a date. I'm trying to give you as much time as possible without breaking any rules of going into reading day. I think reading day is on Tuesday the 8th, so it's either going to be due the 4th of December. Let's tentatively plan on the 4th of December, but no earlier than that.
Okay, thank you.
Okay, sure. Okay, so that is the lab you have coming up, and so the feedback that I got out of a circuits task force, the circuits force, what's it called? The circuits class task force. It's a review of courses in the department that happens every couple of years, and students wanted some more kind of less guided labs and more kind of hands-on work of a design where they could choose values on their own. So I'm going to give you some guidance. Use that guidance. Don't use that guidance. It doesn't really matter. But I want to make sure you have enough to work with here. If you have another way to do this, if you have another way you want to use the parts in your kit to light up 3 lights in the way that I've done here, go for it. Experiment. And you don't have to stick strictly to the guidance. So, okay. So what I'm going to do now is continue with the discussion on microcontrollers. Let's see. Okay, so you should see on your screen now the slide that we talked about last time. So I explained at a top level how microcontrollers take instructions in program memory and store variable data in data memory, and the CPU goes out and fetches instructions and gets data and performs operations. It's all synchronized by the clock, and you can control input ports and output ports. We're going to dig a little bit more into that today. And I wanted to describe a little bit more about ports and peripherals. So what is a port? A digital port is a digital input or output. You'll hear these called I/O, digital I/O, general purpose I/O. I/O is input and output. And typically these digital ports either input or output zeros or ones, which means at the pins of the microcontroller, you would measure 0 volts or 3 volts for a 3-volt logic microcontroller, or 0 volts or 5 volts, right, for the 5-volt microcontroller. And these ports can actually be used to trigger functions of a microcontroller. So you might have things you want to happen really fast, like an airbag sensor triggers that a crash has happened, so that you want to interrupt all the processing. You don't care about tuning the radio and turning on the dome light of the car anymore. You care about firing the airbag. So these digital ports can be used for interrupts, to interrupt regular operation and cause something to happen quickly. The peripherals are generally special capabilities, and I mentioned this last time, like analog to digital conversion, which takes an analog voltage, continuous voltage, and converts it to a quantized voltage that can be represented with bits. There's digital to analog conversion. Take a number, a binary number, and convert it to a voltage, right? So you can do things like create audio waveforms or whatever. There are timers. These are peripherals also. These can read input periods. I showed you that this infrared transmitter, right, your television remote control, it controls the timing and the position of those pulses. Well, you can use timers in a microcontroller to time the periods between pulses and convert that maybe to channel up or channel down. So that's a useful peripheral for communications. And then communications interfaces can be implemented with peripherals, like serial communications between controllers. You know, I mentioned you could create an infrared light pulse stream that would communicate data. You might do that with some kind of serial peripheral communications device inside the microcontroller. And there's also debuggers. So if you've used debuggers in the Arduino, then you know that that's useful. You can connect to your microcontroller and check variables and watch code happen step by step. Okay. And again, if my slides don't match what I'm talking about, let me know.
Professor?
Yeah.
So Oh, I actually think you're gonna go over in this slide. I was gonna ask like what exactly physically like the ports and peripherals are, if there is a physical representation of them.
Yeah, yeah, I'll show that. I'll show that next.
Okay, gotcha. Thank you.
Okay, so here is an example microcontroller. This is a TI MSP 430. It has 64 pins around it, and you see all these labels around the microcontroller. What these are, these are the ports that you can control, or the peripherals, or I should say the interfaces to the peripherals of the microcontroller. I picked an example. So these pins, 59, 60, 61, 2, 3, 4, 5, 6, right, in this table here, they correspond to port 6 of this microcontroller. Port 6 generally in this microcontroller consists of 8 bits, P6.0 through P6.7. You can control each one of these pins, like pin 60. You can control as an output port, you could make it 5 volts or 0 volts with software, with a line of code. Same thing with the rest of the ports. And you can also set them as outputs or inputs. So I could read, let's say, port 6.5. Is there 5 volts or is there 0 volts applied to that pin? And so you could use that value in software to make a decision or control something based on an input. You'll see there are other designations here for these pins. You have A0 through A7. Those are the analog to digital converters of this device. So peripherals actually share pins. So you have access to the peripherals, access to the ports, but some pins are actually shared. They're configured in software. So you'd have to say, okay, I want pin 59 to be an output digital port. I want pin 60 to be an input digital port. I want pin 61 to be a analog to digital converter. And you can do all that in software. And so you can really tailor these chips to the functions that you need. And to do this, you write software to program the microcontroller. You load it into the controller's memory, usually called flash memory. The programming languages that you use are usually C. It's common. So C is a very common language. If you've used an Arduino and the Arduino IDE, and you've written, I guess, what they call a sketch, you've probably used C, and you may have used C++. It's becoming a lot more popular, so you can create classes and objects and all the great stuff that comes along with C++. You can also use what's called assembly language. So assembly language lets you get closer to the actual instructions that happen in the microcontroller, the actual instructions that the CPU executes. What the CPU actually executes is called machine code. So machine code is the set of ones and zeros that are stored in program memory that get fetched by the CPU. So assembly language is usually maps directly to the machine code. So you can really do some low-level programming if you need some extreme speed. If you have to tailor a program to get some really extreme speed for signal processing or something like that. It's more typical for application programmers to write in C or C++. Some DSP programmers use assembly language, and pretty much no one uses machine code. That's what comes out of these higher level languages, is the machine code that the microcontroller can actually use. So what you do is you take a compiler, and it takes a C program or C++ or even assembly, and it produces machine code that can be read by the CPU in the microcontroller. And then, so now you have that code compiled on your PC, and you get some programming hardware, or that hardware might be built in to the board, like on an Arduino, and you download that code to a microcontroller. Okay. So this is an example board. I kind of gave you a preview of this during the last lecture. Here's the microcontroller itself. it cannot operate alone. It usually needs some kind of external clock. Some microcontrollers have built-in internal clocks, but this one has a crystal. So right here, this is a crystal that controls this, it's an oscillator. It creates a square wave along with a couple capacitors here for that microcontroller to execute its instructions and do its fetching of data. There's a voltage regulator on here. This is a voltage regulator down here. This is VR1, 3.3 volts. We'll talk about that in a couple lectures. And there's some support components, right? A power LED. There's some interfaces for communications up here for serial communications. All that stuff's built into this development board for a microcontroller. And you'll see microcontrollers specified with what kind of language. Well, their development environment has some kind of language you program in this case, C, what voltages they operate on, how fast their clocks are, right? Look at that clock speed, 8 megahertz clock, right? Your PC is probably running at, 1 gigahertz, 2 gigahertz. This is running at 8 megahertz because it's meant to control, not crunch data. This microcontroller has 6 I/O ports, which means 6 times 8 bits, 48 individual pins that could be controlled or used as digital sensors. It has several ADCs, digital to analog converters, etc., and peripherals. So there are hundreds, if not thousands, of different types of microcontrollers available depending upon what you need. If you need more digital ports, you can get that. If you need fewer, you can get that. If you dig into this board, what you'll see is a schematic that looks like this. And I'm going to point out some things that you should recognize. Well, here in the middle is the microcontroller itself. It's just drawn as a box with all of its 64 pins, I think, in this case. And there's the support electronics shown on here. At the upper left, this is the power input, right? So this takes in, well, DC or AC. Isn't that interesting? 4.5 volts AC or 6 volt DC. So there's something doing a conversion here. Microcontrollers operate off of DC. Well, look right here. This looks a whole lot like a full wave rectifier, and that's what it is. It will convert AC to DC, and here's the capacitor, a big capacitor that smooths out the rectified signal right there, right? So this looks just like what we covered in class. And there happens to be a power LED right here to show the board is on. When you apply DC to a rectifier, right, full wave rectifier, it just passes the DC through. You get a little bit of voltage drop across the diodes, but it's no big deal because you've got a voltage regulator over here. This voltage regulator we're going to talk about, it maintains a constant voltage output for a given higher voltage input. And look, here's a node voltage. So this is common. You'll see node voltages specified. So right there at that node, 3.3 volts. And then look down here at the kind of the right center, 3.3 volts, 3.3 volts. Those are assumed to all be connected. That's one node, all connected together, even though you don't see a line drawn between all of those nodes, right? Lots of 3.3s here. Same thing with ground. This is more of a European ground, this kind of line, this horizontal line at the bottom of a vertical line. That's a ground. These boxes are more the European way of drawing resistors. Okay, so that's a resistor. What else should I point out here? Right, here's an LED that you can control with a resistor in series. That should look familiar. What else here? Here are a couple voltage dividers, right? This chip needed a couple reference voltages. So if you need a certain reference voltage, you can set R32 and R33 to whatever you need to get a specific voltage at VREF minus, right? Here's one for VREF plus. So you can set those those resistors to get a particular voltage. So lots of stuff we covered in this class are included actually in this schematic. So as I mentioned, you write code on a PC. Sometimes you use an external programmer, unless you have a board like an Arduino board that has a USB built into it. In this case, you need an external programmer, which is one reason Arduino took off. It's a very simple, powerful board that doesn't require you to buy any extra hardware. So, and what you do is you use some kind of integrated development environment with a compiler. Right? You type your code in, you compile it, and then you can run and debug your code. All right, so that's a very top level overview of a microcontroller. I'll tell you, you can, if you're ever involved in a project in the future where you need to sense and control and write some software, in 1 or 2 weekends, you could sit down with like a Microcontrollers for Dummy, Arduinos for Dummies book, or a few YouTube videos, and you really can do a lot with, again, something like an Arduino Atmel microprocessor, microcontroller, and get a lot done. But the fundamental takeaways here are this: microcontrollers are software programmable. You write code, you compile code, you download it. You can assign those pins to different functions, digital ports or analog ports, right? And you can use the microcontrollers to sense and control. Let's talk about doing a little bit of math. How does the microcontroller handle numbers and its digital input and output using bytes? So let's talk about representing integers in a microcontroller or microprocessor. If you use the Arduino IDE, you notice that in C you have to declare what type a variable is, and what that's really doing, like you have to say it's an integer or a long integer or a short integer, and what that's doing is it's actually defining how the compiler interprets the numbers and how many bits are in that number. So if you use, for example, what's called a char or a car, that's a remnant of ASCII where characters were represented by 8 bits. If you use that type of variable, you've created a place in memory that stores 8 bits, and that's what your variable will hold. It'll hold values from 0 to 255, unless you have a signed char, and here are 255 values, or 256 values, but they range from -128 to 127. It's all about how you interpret the values in that word. If you need bigger values, integers, you can use these short integers, and so those are 16 bits, and they can be signed or unsigned. Right? And so you have to know how to interpret the numbers when you have 16 bits, because there's a sign bit that tells you, one of the bits is used as a sign bit, and it tells you whether the number is positive or negative. And if you need bigger numbers, you have long integers and long integers, right? If you need really big integers. So the microcontroller reserves places in data memory in order to store values of different types. Let's talk about decimal numbers, I should say fractional values. So typically, compilers, microcontrollers, they represent decimal values with floating point. There's some DSP, digital signal processing applications, that use fixed point, but it's more common, like MATLAB uses floating point, and usually when you program an Arduino with fractional values, it uses floating point. So in this case, this was for this one compiler where I grabbed this information. The floating point and the double precision and the long double precision, they're all 32 bits. So it's a 32-bit word to represent these values. And this is how floating point works. There's a sign bit, there's an exponent, and there's a mantissa. And let me tell you, don't worry about having to convert these for homework or on a test. I just want to expose you to that this exists, right? You should know that this exists, and it should maybe solve some curiosities that you have about how numbers are stored. So the exponent is 8 bits here, and the mantissa is 23 bits. And the value of the number is -1 to the power of the sign bit, right? So that's either 0 or 1. 2 to the power of the exponent -127 times 1 point the mantissa. Okay, so that's so you can change the fractional value here with the exponent and the magnitude with the mantissa here. So the range of numbering, the range of numbers that you can represent, it's huge. Plus or minus 1 times 10 to the -38, right? That's a really small number, to 3 times 10 to the +38, a really big number, right? So positive or negative. And you'd say, well, wait a minute, why use integers? Why not always use floating point numbers? Well, the answer is that processors, microprocessors, microcontrollers, can perform operations generally faster on integers than on floating point numbers. And so sometimes if you want speed, you use integers. If you only need 8 bits of integers, there's no reason to waste 32 bits, let's say, for a big array of values of floating point. Okay, so that's how fractional values are represented. So when it comes to digital ports, microcontrollers have their inputs and their output ports have limits on the allowable voltage and current. And so exceeding these limits can damage the microcontroller or cause unpredictable results. So, you know, in some future class, if you're using a microcontroller for a project, be careful of these limits. This one particular microcontroller, you could only have below ground by 0.3 volts or above ground by 0.3 volt, or above VCC by 0.3 volts. If you go outside of its power supply range, you can damage the microcontroller. So that's interesting. But what I want to point out here, and for the next couple slides, is that there's a limit, right? There's a limit of current output from a microcontroller. So if you want to, let's say, light up an LED with this microcontroller, it would be a very dim LED because you can only output 6 milliamps, and that would very dimly light up an LED. If you want a bright LED, you need 20 milliamps. So you'd have to have, well, some way to use the microcontroller in order to control something like a driver, right? The current driver that you built in another lab to control higher current, right? That's a great application of a transistor. So back when we were talking about transistor and I was referencing the future, right, microcontroller pins, this is what I was talking about. So if your load needs more current than a microcontroller can provide, one option is to use a transistor. And so this should look familiar, right? Here's the load. You built this in lab, so you could have a microcontroller digital output port that outputs either 5 volts or 0 volts. That should look familiar. That saturates this transistor. It's like closing this switch when you saturate that transistor and lets current flow through the load, right? So you design that resistor value so that the transistor saturates to control the load. Okay, so you've seen that at least a couple times. And then, so there are other options, and there are specialty chips. Now, I mentioned that there are buffer logic gates and inverter logic gates that can take a very small current at the input and handle higher currents at the output. This is one of those. I want to point a couple things out here. So you can control 7 higher current loads with this chip. There are 7 inputs here from a digital output, let's say, of a microcontroller, and there are 7 outputs. And if you dig into this data sheet, what you'll see is this, and I'll get to this in a minute, but assume you have a load. This load could be like one of the segments on a 7-segment display, right? There are 7 drivers here. And so when you let's say put a logic level 1 at pin 1 here, pin 16 will actually go low, right? That's what this inverter is. Pin 16 goes low when pin 1 is high. If pin 16 is low, that means it's ground. Current's going to flow through that load to pin 16, and that's going to sink current. If you look at what's inside of that for each one of these output pins, you see this, and this should look familiar also. Well, partially familiar. You have an output that's not connected to anything but collectors. This is an open collector output, right? We talked about open collector output. The output is either pulled to ground, connected to ground, like this is a switch, or it's left open if these transistors are in cutoff. Okay, so this is like the like the output of the comparator chip that we talked about when we were covering comparators. Don't worry about that diode. We'll talk about that when we get to motors. The reason there are 2 transistors, this is called a Darlington pair of transistors, because you're effectively almost multiplying the betas of these transistors together. So you get a really high current gain. That means you need very little current into the input in order to cause these transistors to saturate and conduct a lot of current. Okay, so that's another way to control a high current load with an integrated circuit. On one of the applications that I showed for a microcontroller, I said, well, there's some input from a switch, like the scale input, to 0 the scale or change the units of the scale. Well, here's an example of how to do that. This is a typical way of applying a switch's input to a digital input port of a microcontroller. And so the common way to do this is use a pull-up resistor so that this node where my mouse is always pulled high, because very little current goes into the microcontroller input. So this node right here would be at VCC until the switch closes. So when the switch closes, it connects that pin to the microcontroller to ground, and the input value goes low. So this is a common way to do that. So when the switch is open, the input to the microcontroller is 1. When the switch is closed, the input to the microcontroller is 0, because that switch connects that microcontroller's input to ground. Now these switches are mechanical devices, and I'll say they're noisy, they're scratchy. They have mechanical contacts that open and close, 2 pieces of metal that touch and separate. And what happens in that circuit that I just showed is voltage doesn't switch very cleanly from, let's say, low to high or high to low. So this is zooming in on that voltage that's going into the microcontroller. And so the mechanical switches cause kind of this fluctuation in voltage when they are pressed and released, and the resulting voltage characteristic is called a bounce, right? Imagine this voltage is bouncing high, bouncing high, bouncing high, finally settling high. And what that can do is that can cause a microcontroller to sense that a switch has been pressed and released multiple times. So if I had like an input high voltage level where this red line is, and I'm counting how many times a switch is pressed, then I might get 3 counts of the switch when it was only really pressed once. So that's not what you want. So what you do is you debounce the switch, and you can debounce the switch in software or hardware. In hardware, you can actually apply a capacitor to smooth out this voltage, right? In software, which is free and takes no board space, The simplest software approach is you would detect a transition from a switch. You would wait a fixed delay, right? So I detect the first transition, I wait a delay, and then I test the input again. And then if the input remains the same, accept it as the new value. Okay, and then a delay of something like a few milliseconds is a common choice. So why do I show you this? Because there's possible in one of your future design projects, maybe your senior design project or something in your systems course, where you might have a switch as an input, and if you get kind of erratic behavior because it looks like you're pressing the switch multiple times and you're not, well, this is an approach you can use to debounce a switch. Okay, well, it looks like we've finished right on time. It is 6:10. So remember that pre-lab 10 is not due on Friday. This is the last lab. Lab 10 will start this week and will continue for a couple weeks. There's a quiz posted and it's due on November 20th, so take a look at that on Canvas. So thanks again for joining class. I'm happy that everybody's joining the live lecture. I think it's good to get questions out there and be able to interact. I hope it's working out well. Let me know if anything isn't working out well, and I will do my best to fix it. So I will start office hours in about a minute once folks drop off. If I don't see you at office hours, I will see you next time. Have a good night.